about what is a photodiode, classification of photodiode. Further, we have seen that there are some disadvantages associated with PN photodiode. Before going into other types of photodiode, we will discuss about the performance parameters of a photodiode. So what are the performance parameters of a photodiode based on which we can judge the performance of a given photodiode? Generally, the critical performance parameters of a photodiode includes responsivity, quantum efficiency, dark current, and response time. These are the most commonly used parameters to judge the performance of a photodiode. We will discuss one by one. First, we will see what is responsivity of a photodiode. Let us see what is the definition of responsivity first. The responsivity of a photodiode is defined as the photocurrent generated per unit incident optical power at a given wavelength. Basically, for different wavelength, if we will calculate the responsivity, we will be getting different values. Responsivity means how the photodiode is responding to the incident optical power, and the response can be judged by looking into the photocurrent generated, right? Because that is the response which is given by a photodiode. The photodiode, basically when optical power or light is being incident on a photodiode, it will either produce a voltage or a current. So the responsivity is the ratio between the photocurrent generated and optical power. If IP is the photocurrent generated and P0 is the incident optical power, then the responsivity can be written as R lambda is equals to IP by P naught. Here IP is the generated photocurrent and P0 is the incident optical power. Further, here I am writing R lambda because if the wavelength of the incident light is changing, then the responsivity of the photodiode changes. So this represents that the responsivity depends on the wavelength of the incident light. Now can you tell me what can be the unit of this responsivity? Here you can see the responsivity is a ratio between a current and a power, and generally the unit of current is ampere and unit of power is watt. So the responsivity is expressed as ampere per watt. This responsivity is a measure of sensitivity to light. How the photodiode is sensitive to the incident light, that can be measured through this responsivity. Further, this also measures the effectiveness of conversion of light power into electric current. How effectively the photodiode is converting the incident light power into electric current, that can also be measured through this responsivity calculation. As I have already told, the responsivity varies with the wavelength of incident light, applied reverse bias and temperature. So these are the physical quantities based on which the responsivity will change. Now coming to the second performance parameter, that is quantum efficiency. This is defined as fraction of incident photons which contribute to photocurrent. Let us understand this line. I have already told you that all the photons, they cannot contribute to the photocurrent, because we have seen that if the energy of the incident photon is more than the energy gap of the material, then only it will lead to electron hole pair generation. If it is less than the energy gap, it cannot generate the electron hole pair. And those electrons which are coming from this electron hole pair generation, that leads to photocurrent. So if the energy of the photon is less than the energy gap, that will not contribute to the photocurrent. At the other hand, if the energy of the incident photon is more than the energy gap of the corresponding material, that will contribute to the photocurrent. That means if we are incidenting 100 photons, out of that 100 photons, all might not be contributing to the photocurrent. If out of those 190 photons are having more energy than the energy gap, then that 90 photons will contribute to the photocurrent and rest 10 will not contribute to the photocurrent, right? So this quantum efficiency tells us about the fraction of incident photon which is contributing to the photocurrent. Quantum efficiency can be written as the ratio between rate of electron generation by rate of photon incident. How much electron hole pairs are generated and what is the rate with which we are incidenting the photons. If we will take the ratio, that will give us the quantum efficiency. Like earlier I told you, I have incidented 100 photons, out of which 90 are contributing to photocurrent. That means these 90 photons, they are having more energy as compared to the energy gap. That means here I can write the efficiency as 90 by 100 because I have incidented 100 photons per unit time and the photocurrent per unit time is 90. Means this 90 electrons, they are contributing to the photocurrent. So it is 90 by 100, so I can get the efficiency as 0.9. If in percentage, that will be 90%, right? Now let us write the expression for this. This rate of electron generation can be written as IP. This is the photocurrent generated divided by the charge of the electron. And rate of photon incident, that can be written as P naught. This is the total power incident divided by the power of a single photon, that is h nu. So this gives us the rate of photon incidence. So rate of electron generation is IP by Q and rate of photon incidence is equals to total power incidence, that is P naught divided by h nu. This is the energy of a single photon. Just by rearranging this, I can write this h nu will go up. So it is h nu IP by Q P naught. Further here, if you can see this IP by P naught, what is this? Just in the before slide we have seen that this is nothing but the responsivity R lambda. So I can write the quantum efficiency eta is equals to h nu by Q, and in place of IP by P naught I have written R lambda. So here you can see the quantum efficiency is directly proportional to the responsivity. Thus, this is the relation between quantum efficiency and responsivity. From here you can see this responsivity is equals to IP by P naught. So for a photodiode we can measure IP, we can calculate the incident power, right? So from this we can calculate the responsivity, and using this responsivity we can calculate the quantum efficiency of that photodiode, because here h is the Planck's constant, nu is the frequency of the incident light, and q is the charge of electron. So by substituting all these values we can calculate the quantum efficiency, and R lambda we can calculate directly from the device by measuring IP, and we know the value of incident power. So we have seen the quantum efficiency eta is equals to h nu by q into R lambda. Here what I am doing, h by q, in place of this nu I have written c by lambda, because this is the frequency of the incident light and we know that the frequency can be written as velocity by wavelength. So it is the velocity of light c by lambda of the corresponding incident light into r lambda. This can be written as hc by q, and I have just written this one r lambda by lambda. This hc by q, these are constant quantities, right? Because Planck's constant, velocity of light is also constant, q is the charge of electron. So this whole quantity is constant into r lambda by lambda. Now let us see what can be the value of this quantum efficiency. This r lambda, if we am taking that in terms of ampere per watt, then eta is equals to 1.24 into r lambda by lambda, and this value will be 1.24 only when I am taking the value of wavelength in micrometer. Sometimes if you are taking the value of this wavelength in nanometer, then this can be written as 1240 into r lambda divided by lambda. Here the difference is, if I am multiplying with 1.24, then I should take the lambda in terms of micrometer. If I am multiplying with 1240, then this wavelength should be considered in terms of nanometer. And this value I have obtained by just substituting the values of h, c and q. Further, this eta is equals to h nu by q into ip by p0. This is the expression we have seen in the previous slide. From here I can write ip is equals to this q p naught will go that side, h nu will come to the denominator. So it is q p naught by h nu into eta. So this is the expression for the photocurrent, because this ip is nothing but the photocurrent, right? From here you can see that this photocurrent is directly proportional to the quantum efficiency. If I am increasing the value of eta, then this ip will also increase for a particular incident power, right? And always we know that the efficiency can maximum be 1. Okay, so what will be the maximum photocurrent? I have to take this eta as 1. So taking eta as 1, I can write the maximum photocurrent is equals to q p naught by h nu, where this p naught is the incident power. And here, for this condition to be satisfied, this value of quantum efficiency should be equals to 1. That means all the incident photons are contributing to the photocurrent. That means each incident photon generates one electron hole pair contributing to the photocurrent, because eta is 1. None of the photons are getting wasted. All photons are having energy more than the energy gap, and they are generating electron hole pairs and contributing to the photocurrent. In that case, we are getting the maximum photocurrent, which is equals to q p naught by h nu. Let us now go back to responsivity and see some important results. So this is what we have obtained. Quantum efficiency is equals to 1.24 into r lambda by lambda, where this lambda is in micrometer. From here, this r lambda is equals to this lambda, if you will take this side, it is eta lambda divided by this 1.24. Okay, so from here we can get this r lambda is equals to eta lambda by 1.24. Further, here I am telling once again, this lambda should be in micrometer. From here you can see the efficiency of any photodiode, that should be constant. Okay, so if this is constant 1.24, this is also constant, that which is the physical quantity based on which this r lambda will change? That is nothing but the wavelength of the incident light, that is lambda. So r lambda is directly proportional to the wavelength of the incident light, that is lambda. So from here it seems that if we are increasing the value of lambda, the responsivity will also increase. Will it increase indefinitely if I am increasing the lambda slowly? Then whether this R lambda will increase continuously, let us look into that. We know that the photons will contribute to the photocurrent if their energy is more than equals to Eg, that is the energy gap of the corresponding material. From here I can write Ep is nothing but Hc by lambda, that is h nu, and h nu can be written as Hc by lambda. That should be greater than equals to Eg. From here I can write lambda should be less than equal to Hc by Eg. So there is a constraint on the value of the wavelength I should consider. I cannot increase the value of lambda indefinitely, because this is the constant I have to keep in mind. Lambda should always be less than equals to Hc by Eg. Okay. So for a particular material, this Eg is constant and always H and C are constant. So for a particular photodiode, this value of lambda should be less than equals to this one. So I cannot increase the value of lambda beyond this. So the maximum allowed value of the wavelength is restricted by the value of the energy gap of the material of the photodetector. Now coming to the third parameter, that is dark current. We have already seen what is dark current in our previous lecture, right? So the dark current is the reverse leakage current in the absence of light radiation. When we are not incidenting any light on the photodetector, still there is a leakage reverse current which is known as dark current. Thus, to have a better photodetector, we need to keep the dark current as less as possible. So what are the quantities which can control the reverse leakage current? Let us look into that. The amount of dark current depends on reverse bias voltage. Further, it also depends on the resistance of the circuit and ambient temperature. So these three are the most appropriate parameters which can control the amount of dark current flowing through the photodiode. Now coming to the fourth one, that is response time. From the name itself you can see response time means how quickly it is responding to the incident light, because photodiode is responding to the incident light, right? So you will be preferring a photodiode with less response time or more response time. Obviously, the preferred photodiode should have less response time. So the response time is a measure of how quickly a photodetector responds to the change in the intensity of the incident light. A good photodetector can detect or respond to the change more quickly. So what are the parameters on which this response time depends on? It depends on width of the depletion region. If the width is more, then the response time will be less. Further, it depends on the band width of the photodiode and transit time of the photo carriers. How much time it is taking to transit from the depletion region to the circuit. Further, it also depends on RC time constants. So these are the parameters on which response time depends on, and we will prefer a photodiode if it is having less response time. That is why we will be discussing about pin photodiode and avalanche photodiode, which are having less response time as compared to PN photodetector. In the next video, I shall come up with some more interesting things about photodetector. Today we will stop here. Thank you all for your listening. If you like the content of the video, please press the like button and share the channel link with your friends. Further, don't forget to subscribe the channel. Thank you all.